extremely powerful is very difficult to use. Operating systems have been developed to help the user to use the system. The foremost responsibility of the operating system is to provide a hospitable interface to the user and a comfortable, convenient runtime environment. Let us try to have an overall picture. Here we have a bare machine. What has been done is that on the bare machine, a layer of software has been put. We call that a runtime environment. And over and above that, we have another layer of software shown in green. This is a user interface. When a user approaches the system with a job, say run program P, then the user interface sets up a dialog with the user. The program P is accepted and loaded, and the program P executes. Say while executing that program, the program wants to read some data, say read A. Now, reading a data from an input device as such is a very mundane job. The input device has to be energized, the bit stream will come, that has to be interpreted properly according to the format given in the read statement, and then that had to be delivered in the location the program P wants. Now, if a programmer has to do this job, then naturally it will be too tough for him, and many of us, if such mundane jobs have to be done, would have possibly left programming altogether. That is why in that runtime environment, we keep, the operating system keeps that input-output system. That request that read A is then put to this runtime environment. The input-output systems takes over, reads the input, and delivers the whatever has been inputted to the program. That way, the programmer is relieved of such inputting, outputting at the barest minimum level. He can remain at the higher level. He only says read A, but many such operations are done by the runtime environment itself. Now, for simple devices like keyboard, this inputting or say printer outputting may not be very difficult, but if we have a disk drive from which we'll have to bring in informations and put informations into the disk drive, many more programming efforts are needed, and the runtime environment relieves the programmer, as I have said already, of all these jobs. Another responsibility of the runtime environment, is that if there are other programs, let's have another program here, P2, and P wants to communicate with P2, instead of directly communicating with each other, which turns out to be a difficult job, that communications is directed via this extended machine. Therefore, this bare machine, with this runtime environment support, we call an extended machine that contains such software for input-output systems. Sometimes we call them BIOS, basic input-output systems. It also contains many resource management programs, including this communication part, and then we call them sometimes the kernel, depending upon the specific operating system. Now, that user interface that the operating system has to communicate with the user is not a very technically complicated job, but it's essentially a job which has to be done very nicely. Therefore, the design aspect is very important so that the user finds it comfortable to use and user finds it convenient to use. Now, this entire software, this layer, is sometimes called shell, and it also calls the utilities and the applications when needed. For example, say the programmer wants to compile a program. Then it requests to the shell to give a compiler, a translator at his disposal that is handed over to the program, and that compilation or the translation is done. The applications involves, okay, application solutions include compilers, database systems, business programming, games, and many more other applications. Similarly, if necessary, when the user wants, the utilities are brought in and the programmer is given access to these utilities. That utilities include text editing, displaying online documents, and such other programs. Therefore, this entire thing is essentially an extended machine view. The programmer never sees the bare machine. He sees an extended machine. He talks with that user interface, and that user interface, as I said, should be very friendly. Sometimes it is menu driven. That means a set of menus are given. The user simply ticks that what he wants, and that activity is taken. Sometimes it is command line driven. That means user gives a command, okay, and that command line is interpreted, and that particular job is done. Here we have, of course, taken a simplistic view of the operating systems. We say that there is one layer here and possibly another layer here. But actually, there will be many more layers, the details of which we will discuss when we come to the operating system design and operating systems working. Now, there is another view of the operating system, and that view is as a resource manager. The computer has many resources at its disposal, say the processor, the memory, then I/O devices, and lots of informations that are entrusted with the computer. Now, the second job, and no less important for the operating system, is to manage these resources properly. Let us see what's the job so far as the operating systems as a resource manager is concerned, right? Say, as I said, the system resources are processor, memory, the devices, and that information. And the jobs include that management functions include that one has to keep track of the information, then decides who gets and how much of this resource, then allocate the resource and deallocate on completion, or sometimes forcibly deallocate the resource. Let's see a processor. If it's a single processor system, and if there are more than one job is there in the system, in that case, the operating systems has to keep track that whether the processor is busy or the processor is occupied or has been taken by some job. One thing let me clarify here, that the term job, the term process, and the term program initially will be used interchangeably, but naturally there are finer distinctions amongst them, and we'll talk about the distinctions when time comes. Now, coming back, say the processor, and there are more than one job, as I said, then the management function includes that the operating systems keeps track of the status of the processor, whether it's occupied or not. Then amongst the jobs which can take the processor, decides who gets it and for how long. Here how much is basically how long. Then allocate the processor to that particular process, and on completion or temporarily it deallocates the processor so that it can be given to some other process. That is also true for memory, that if I have more than one job, the operating system has to decide that which portion of the memory who will get. On completion, that memory has to be taken out of that job and to be given to someone else. And also it has to keep track of the memory, that which portion of the memory is free and which portion of the memory is occupied. Now let's go one after the other. Say first we come to the processor, then memory, then devices, and then the information. Right? Let us take a process life cycle to see that what are the things involved. So far as the processor management is concerned, basically which in turn means the process management is concerned. Now, when a job comes, it's in the new state. This is basically a state diagram, state transition diagram, as a job moves through the computing environment. A new job has come, therefore it's in the new state. Now, when the OS sees that all resources that may be needed by this new job can be given to it, then that job is admitted into the ready state. By ready state, it means that now if it gets a processor, that job can start executing. Now it's in the ready state. Say the processor is free, that job is then dispatched to the processor and it is in the running state. Now while running, it may ask for an input output. Now when the input output is being done, it's no use that that process has to be on the processor, and therefore it can be taken out of the processor and it's in the block state. That means it is blocked due to that input output operations being done. On completion of that input output, it can come out of the block state and come back into the ready state once more. Now, it goes on for several cycles possibly, and then sometimes its job is over, okay, and then it is released and come to that exit state, right? Therefore, the process goes through these states one after the other as the situation happens and ultimately comes to the exit state. But say while running, if there is any problem that job has done some illegal operation, in that case, that process can be taken out of that systems altogether forcibly and can be put into the exit state as well. Now here, one important thing can be examined, and that is, say for example, if it is a single processor or a situation and a single job is there, then when that single job is blocked, that processor is free. And if that processor is free, that time is wasted. Therefore, why not include into the system, admit into the system more than one job simultaneously? That means in that case, the situation we call multi-programming, more than one job simultaneously is within the system. Now in that case, when one job is in the block state, another job can be dispatched from the ready state in the running state. For that, what we can do is this, that we can keep a queue here. That job comes in, we keep in the queue, and as the processor is free, a job is taken out of the queue and dispatched to the processor. Now, under that situation, it may also happen that more than one job is blocked due to the I/O. That means there may be many jobs that are blocked here. When the cause for blocking is over, that particular job is taken out of the block state and put into the ready queue once more. This is the ready queue. Now, situation may also happen that a particular job which has been put into the running state is does not do much of I/O. That means it's in the running state for quite a long time. It can be in the running state for quite a long time. Now, if that be the situation, in that case, the other processors will be waiting either in the ready queue. Some will be waiting in the blocked queue, but we are not bothered right now for them. Many processes may be waiting in the ready queue. And in that case, what is done is that process is taken out forcibly of the running state, that means forcibly out of the processor, and puts back in that ready queue. For that, what is done is that whenever a process is put into the running state, into the processor, a time slot is allocated to it. If within that, say for example, say 1 microsecond, if within that time that process completes its job, okay, and does not do any I/O, then on that timeout, it is brought back into the ready state, therefore it's pushed into the ready queue. But if within that, say it asks for an I/O, then automatically it comes to the block state, remains in the block state, and on the I/O done, it goes to the ready state once more. Therefore, this is in fact the picture where you can see that the processor, as I said, that I am assuming for the present that there's only single processor, that the processor can be kept busy. The memory also can be better utilized, because in that case, more jobs are there, and if we have a huge memory, a particular job may not need that amount of memory. Therefore, if we admit more number of jobs, then the memory also can be better utilized. Now, let's see if we come back to the other instance, other management operation, that means the memory management. Say, as I said, say this is the memory. That memory management in that case has to be done if there is more than one job that is in the system. That is if I am doing multi-programming. Okay. What initially the operating system is in the memory. So 4 jobs are there: J1, J2, J3, and J4. J1 has come first, say, and has been given this memory contiguous. Then J2 has come, it has been given this memory. J3 has been given this memory, and J4 has been given this memory. And this portion is small enough that it cannot be given to any other job, and therefore, for the time being, this portion of the memory is wasted. Now, J3, right at this time, say, if we come to this process life cycle model, say J3 possibly now is in the running state, right? If J3 is in the running state, we'll have to look into the security and protection of the other jobs from J3. By that I mean, for example, J3 may try to either unintentionally, inadvertently, or intentionally go across its boundary, that means this one and this one, and try to access something from J2 or J1 or J4, or even try to access something from the operating system itself, right? For that, what is done is that a base register is kept, which points to the beginning of the J3's memory assignment, and a limit register is kept, which points to the highest memory location the J3 is occupying. Now, when we do it this way, we call it this memory management partitioning scheme. Now, if the J3 accesses the memory location within its purview, that means within its address space, then J3 moves on smoothly. There is no problem. Now, if J3 wants to go beyond its boundaries, either in the lower side or in the upper side, that is dynamically compared all the time, the addressing is dynamically compared all the time with the base or the limit, and access violation is immediately detected, an interrupt is generated, and the operating system takes hold of the control, pushes J3 out, telling that that access violation has taken place, and the job is put into the exit state. Then forcibly it is taken out of the running state into the exit state. Otherwise, say J3 goes through this life cycle. Similarly, J1, J2, J3, and J4 also goes through this life cycle. Now the situation is, after some time, say J3 is over. Okay, J3's operation is over. In that case, J3 is taken out, that memory portion turns out to be free, and it can now be given to, say, some other job, J5. Okay. Now, J5 naturally will not exactly fit the J3's memory space, and possibly some space here will be left vacant. By vacant, I mean cannot be utilized. Now, it goes on. Then J1 will be finishing its job, some new job will come in over to here. And if it goes on this way, after some times what will happen is that we'll have a situation like this. There are, say, 1, 2, 3, 4 jobs. There are these shaded, red shaded areas in the memory which are not being utilized. Okay. It may so happen that if we add up these areas, okay, this is sufficient to hold a job, but individually they cannot hold a job. Such a situation we call fragmentation. And when fragmentation takes place, the operating system has to do something about it. What naturally can be done, that all jobs can be pushed up. A bigger area here can be created, free area can be created, and that free area can be given to an incoming job, so that one more job can be accommodated. Now, this is a primary memory management scheme, okay, and the operating systems has to do all these jobs, okay, to which, like, say, for example, it has to keep track of which are the areas of the memory that is free, which of the memories are occupied. Whether a new job comes, memory can be allocated to it. If it can be allocated, it is allocated, and it has to be deallocated either on completion or forcibly if it does some violating job, okay, which affects other users, and then that area should be declared free and should go back to the pool from where that area can be allocated to a new incoming job. Now, this is one scheme, the partition scheme, where if necessary, you will have to push jobs, okay, clear bigger areas. Now, you see that just compaction, pushing jobs up, which we call a compaction. Compaction is not very easy. As we'll see later on, that compaction involves time naturally, but over and above that, compaction may need that changing of instructions addressing, okay, of many jobs, okay, of the jobs. In that case, it entails a good amount of operation, and therefore, if it can be avoided, it should be much more efficient. Now, therefore, let us in brief discuss another memory management scheme, which we call a paging scheme, very widely used. Okay. Now let's see. Just initially assume that there is this job J1, which has been brought in. Okay. This is the jobs address space. What we do is this: the jobs address space we divide into pages. Say this job consists of 4 pages. page 0, page 1, page 2, and page 3. The page sizes depend upon the operating systems and the computer hardware. Generally, a 4K page is considered to be good. Now, say this is the memory. Okay, this is the actual physical memory. The memory is divided into equal sized blocks. Once more, if the page size is 4K, we make the block size also 4K. Now, what is done is that it need not allocate the entire job's address space in a contiguous memory location, which was done in the case of partitioning scheme. A contiguous memory location was allocated to, say, job J1. What is done is that page 0, say, is allocated to the block 10. You see that memory block, we have numbers, say 10, 11, 12, 13, 100, 101, each of 4K size. Therefore, one page fits into a block. Therefore, page 0 is fitted into, say, block 10. Page 1 is fitted into block 13. Page 2 is fitted into block 102, and page 3 is fitted into block 522. You see, we have created a page map table where we have kept track of or map of which page of job 1 has gone to which memory block. Now, when the program J1 is executed, whenever it accesses something in P2, say, the mapping mechanism, okay, a convenient technique involving both hardware and software will map it into that 102 block, and that particular location is addressed, and it is accessed. Similarly, if it is coming to P3 and trying to access some informations in P3, okay, then it is mapped into block 522 in that memory, from where that corresponding word is taken out or accessed. Now, this has a advantage. You see, for example, say another job comes into the system, immediately its own page map table can be created, saying that what are the blocks that are free in that entire memory. A page map table is created, and job 2 can immediately fit in. Now you can see immediately that the operating system in that case has to keep track of what are the blocks that are free and what are the blocks that are occupied by jobs, and which jobs, which page has been accommodated into which block. Now, once this picture the operating system have, and once a job is brought into the system, the page map tables are created, the job can go ahead executing its program without any problem through this page map table, mapping through this page map table. Now, this paging technique has an advantage that you don't have to compact. So, for example, now this job 1 is over, this page map table is immediately written off. All these blocks that page was occupying, that jobs pages were occupying, are declared as free and goes back into the pool. When a new job comes, a page map table is created, and from that pool, the free blocks are taken, and the page map table is created for the new incoming job. It has a further advantage. Further advantage is that you can see, say here, that initially to start with, job J1 needs only page 0 and page 1. In that case, that page 2 and page 3 need not be loaded into the memory at all. They can be kept in the disk storage. Okay. And the job J1 can start with page 0 and page 1 only. Subsequently, when page 2 is needed, only then the page 2 can be brought from the secondary, from the disk storage and put into the memory, and a page map table entry is created. For example, 102 say that page 2 was not needed initially, it was not brought in, therefore this entry was not there. Okay, and when page 2 is needed, page 2 is brought in, say 102 block was found to be free, that page 2 was put into block 102, and then the job can start executing once more. Therefore, you see that the operating systems has a role here. The moment the job finds that the page 2 is not there, it automatically informs the operating system. It immediately takes hold of the situation, bring in page 2 from the disk, loads into 102, updates the page map table, and then job 1 is allowed to go free. During this intervening time, the job G1 may go to the block state because of paging IO. Now you can see immediately its repercussions immediately is manifold. One important thing is that if I have to run a job, I don't have to have the entire memory that is to be allocated to a particular job. And that leads to what we call a virtual memory. By that, we do not have to be limited by the size of the physical memory to run a particular job. The job may be much bigger than the physical memory that is at our disposal. We start with only that portion that is necessary to run right now, and when the other portions of the job is needed, they will be brought into the memory, and the control will be handed back to the job once more. If the operating system finds that no block is free, then it will take a decision that a particular block will be made forcibly free. The content of that block, say of job J2 occupying this, it will be forcibly made free. The content of this particular block will be taken out from the memory and put back into the disk storage in that job 2 space, so that this is now free and that will be allocated, say, to job 1. That way we get what we call virtual memory, a situation where one can think, and user can think that an infinite amount of memory possibly is available with him. He or she need not restrict himself or herself with the physical limitation of the memory. Okay, that is another memory management scheme, paging scheme. The details of this paging scheme, the hardware needed, the software support that has to be provided, we'll discuss when we come to the uh, detailed discussion of this memory management scheme, right? Now, there are another important resource that are entrusted with the operating system are the IO devices. Now, there are many IO devices that is connected to the system. The operating system has to keep track of that what are the devices that are available with the computer right now, what are the devices that are online, and when a particular process needs a device or some IO to be done in the device, then that device are to be allocated to that particular process, or the IO is done, and on completion that of IO or the necessity of the device being over by the process, the device is deallocated and returned to the pool. So for example, a particular computer system say has 5 tape drives. Okay. Now the different programs may ask tape drives. Naturally, the operating systems will go on allocating the tape drives, and on completion, the programs will go on returning the tape drives. The operating systems will accept the tape drives back into its pool. Okay. Now, say sometime when a particular program asks for a tape drive, it may so happen that no more tape drive is available with the operating system. In that case, it says that no more tape drive is available. You wait till a tape drive is released by another job, and then it will be allocated to you. It is put into the wait state, into the block state. It's blocked for device being not available. Now, that may lead sometimes to serious problems. And what are the problems? That means the device not being available may lead to some serious problem. And what the problems that can be there, we'll discuss in proper time when we come to the details of it once more. Another thing is that some devices are there, okay, in a system which cannot be made attached to a particular program. So, for example, you have a printer in a system, okay, and many programs are running. All of them will try to print something, and if the if the printer is attached to a particular process, in that case, other uh, processes cannot go on. Possibly it will wait for some time for the printer to be free, and therefore the printer cannot be attached to a particular process that way. Now, the printer cannot be allowed to be accessed by all the processes simultaneously. In that case, say job 1 will print one line, then say job 2 will print another line, and job 1 will print the next line, and so on. You see, and the job 2 possibly print will say another 3 lines. Now, all the outputs will be intermixed, and in that case, one has to sit with a scissor, then cut the different lines, paste it together, and give it to the different users, which is not possible and which is naturally not done. What is done in such situations is that what we call spooling. Now, the spooling is simultaneous peripheral operation on line. Okay, the simultaneous peripheral operation. No printing job is done immediately. The printing is in fact translated into a file in the disk. Okay, for example, this is the file that is being prepared for job 1. Another file, the backup, will be prepared for job 2 as the printing goes on. Okay, and at the end of the job 1, this file will be printed out to the printer. Okay, there are some more things are involved in it. Okay, some details have to be discussed later on. Now, that goes to the I/O devices, the management of I/O devices. Okay, and one more important thing that the operating system has to do is to manage the information. Now, we call a file where we keep a collection of information for a particular, possibly for a particular job. Now, this file is kept in the disk. Okay, the disk is divided into blocks. For example, a disk can be 4 gigabyte, 9 gigabyte, 16 gigabyte. It's quite a huge amount of information that can be kept in the disk. To access information in the disk is divided into blocks. Okay, here we have shown a file where it consists of several blocks like this one. Okay, say this is a block of information, this is a block of information, this is a block of information, and that entire blocks of information taken together consists of file. Now you see that to get an information from the file, one has to know that where the file is. For that, a directory is kept. Okay, so this is a directory. The directory contains the informations regarding the locations of the file. Like, for example, this is a file, the location is pointed to by from this here from the directory. This is another file whose locations is pointed to from here, and so on, right? Where the directory is, that information is kept in the root. Okay, that root points to the main directory, and it can be, the entire thing can be a hierarchical file system, which means a directory can point to another directory, this can point to another directory, and each directory can have the locations of the files, like this is the file 1, so file 2, file 3, the locations of directories also. So if you want to file 1.1, then you'll have to come to the directory 1, then come to the file 1.1, and then get the file. These total informations regarding the files that are distributed on the disk, which is a huge memory area, is kept through this directory system, and the operating systems has to manage this information, okay, through this directory system. Now, this is as I said, this is a hierarchical file structure. There can be other structures also, uh, so far as that information management is concerned, right? Now, one important thing over that directory or file structure is this, that the allocation of the file. So, for example, here we have assumed a contiguous allocation in the disk storage. That means contiguous blocks of the disk space have been allocated to a file 1. It's not necessary that contiguous allocations have to be given to a particular file. It can be linked. That means, say this is a directory entry. From there it comes to this block, then it comes to this block, and this comes to this block, and it comes to this block. That means it's a non-contiguous allocation. Blocks have been taken as is obtained, okay, as it finds it free. The operating system finds it free. The blocks have been allocated to a file, and that way that file is developed. Here it is a mapped one. That means the file is distributed over these blocks, and which particular block exists where, that is kept through this map. Okay, for example, the first block is here, the second block is here, and so on. In that case, once more, it need not be contiguous. Now, file allocation or the information management is very important responsibility of the operating system, and one has to deal it very carefully, very efficiently, so that a program or an application runs efficiently. Now, one more thing that we should discuss here, we should at least mention here, is this: that the operating systems are classified according to the way that it handles jobs. We know about single job. That means there is only one job in the system. Okay, in that case, operating systems are responsibility turns out to be much less, but naturally it has to do all the extended machine operations, right? Now, we have talked about the multi-programming already, so that resources are utilized better, okay? More jobs are inducted into the system. Now, that may sometimes need time sharing in the case of an interactive job, so that a particular job will not monopolize over the processor. Time slices are allocated when a process is dispatched to the processor, okay, and on completion of the time slice, the process is brought back into the ready state, okay. Mainly in the case of an interactive job, such a situation is done, okay. Now, nowadays, no computer systems work in an isolated environment. Mostly they are connected to a network. In the case of therefore, the operating system has to take some responsibility of networking as well. By I mean that, for example, say a particular user wants to access another another computer in a network which is in some other location. Then in that case, operating system should help him to go to their system, use their system, okay, and log on to the system, or use a system by sending a program, executing it, and bringing it back. Okay. There is another classifications we call the distributed operating systems. The difference between the network operating systems and the distributed operating system is this, that network operating systems, the user is aware that a network exists, and in the case of distributed operating system, the user is not aware, is not made aware that the network exists. Okay, it can just ask for a service and it gets a service. And then the real-time operating system, where you will have to honor the time bounds of your response. That means if something has to be done and some request has come from some device, then it has to be honored within a pre-specified time. Now, this is in fact all the classifications that we have. We have not taken into consideration some more, like a parallel operating system. Okay, I mean operating systems for operating systems for parallel systems. We will talk about all of them in detail when the time comes.